Okay, so very good evening and warm welcome to this lecture on tensor calculus as we are proceeding from yesterday. So I would like to add a few things today regarding the tensor calculus. Before we go ahead, let us look quickly into what we actually covered yesterday. Then we have got a lot of topics, important things to cover up as of today. So here is a kind of I would say, quick recap. So we looked into the what is the concept of a tensor. We looked into certain features of the tensor. We also looked what is the mathematical, definition of a tensor. Then from we looked into what are the important features of the tensor, rank of a tensor, and the shape of a tensor, and how the things actually changes from one part of the coordinate system to the second part of the coordinate system. And also importantly, we saw that how the stretching informations are stored, how events actually should be, a kind of a uh, invariant in part of the changes. Tensors are actually metrics which measures something which is something very invariant. So all these things we covered up, and we are going to cover up something very important today. Those who are missed those things, I think it's a good point to work it out. We saw that the initial work of the tensors actually started with what is called the study of crystals, because the study of crystals are the first thing which started with the study of tensor, because it was for different dimensions, size, etc. From there, we came to know that if I heat a particular glass, then it would expand in only one direction, whereas a crystal would expand in different directions. And that is the reason when we need to have a tensor, because we can understand how things will actually operate. Now, I would like to go that why should we study tensors? What is the actual need for the study of tensors? And then I'm going to show you today that tensors are actually something which are also coming from the concept of special theory of relativity. Yes, I've got something important for you which I would like to share. Last time, yesterday, I was not being able to do that. So the reason that we should study tensors, now this is very important for all of you who are watching this, and not only for the study of your tensors in MSc, BSc, mathematics, special paper, etc. But as I told you that how a deep study of tensors can actually change your career in different ways. Take it from me. Last year, I think I have told you I was in Bangalore. This year also, I think next year, January, I would be going, because I'm in the board of the directors, where I sit down, talk to people when they're taking interviews in different campus. And actually, I watch out that what are the career trends that are going on. So, okay, Pranam. Okay, so here is a very quick note. Don't take me wrong, but this is something I won't repeat it again and again, because I feel bad, to be very honest. Two things I have noticed in young students which is very missing. First of all is that you are very good in terms of physics and mathematics. You are great, excellent in terms of making mathematics, etc. But you lack in terms of communication. You lack in terms of writing a resume. You don't know how to sit in front of the interview and really talk. So here is a quick note that tensors that we are dealing today will also lead to data science, machine learning, AI, etc. The way Google Bard is updating every day, I'm watching those updates, etc. I can tell you, learning tensors deep into the deep mathematics is definitely going to take your career better. But all my dear students, you're just like my children. I would like to tell you, please work on your communication skill. I hope do you understand? You can put up a yes or no. And don't take me wrong, because I'm telling you the hard fact of reality. How to write a proper resume, I find that there is a lack. Yeah, Atharva, good evening. So I think you will all agree. Don't take me wrong, I'm not criticizing, but I have never told those things. But when I receive emails, when I receive communications through WhatsApp, I see there's a lack of a proper communication in English. Now, you might be saying, sir, this is a tensor class, don't teach us how to talk. But this is also a part, because the objective is to get a good job, a research, a scholar, or a lecturer. So all those who are watching, I would request all of you to watch my videos or not only my videos, other videos, please work on the communication skill. In Bangalore, in Hyderabad, especially in Mumbai, when I went there, when I saw people, the students are failing because of their communication. The students are failing that when I'm asking, okay, Atharv, why do you want to become a physics teacher? Why do you want to take up maths as a career? Whatever they're telling the truth. But the problem is that there is a lack of communication. Whatever I'm thinking, I'm unable to take. I'm not saying I am a great communicator, but I also teach English in my college, communication skills, so that you can clear in the interview. I was also thinking of creating a channel where I can teach you how to communicate, but I'm so sorry, I'm too tied up with physics and mathematics. I don't think it would be a near about plan. But my only request to all of you is that don't take me something wrong. I hope you understand, but please work on your written and communication skill, because this is very much required in order to secure a job. I hope that you take it in the correct spirit and the right spirit and don't feel bad or unhappy, because I find there is a huge amount of lack of communication. It is not you have to speak very fluently using Shakespeare's or great English, but whatever you are saying should be distinct, should be clear, and should conceive the ideas. Can you please put up your thoughts in the comment box so that I do not feel myself guilty or you feel good? Please do let me know in the comment box right now. Let us go ahead with what we are learning. So first of all, it is that tensors are used to describe the curvature properties of manifold. That means those who will be taking up differential geometry in the near future can take up tensors also. Linear algebra is very important because tensors are basically used in linear algebra. So remember that if you're learning linear algebra up to a certain extent, you need to have a concept of tensors. General relativity, obviously, because you might have seen in my numerous videos that general theory of relativity relies on tensors. And quantum mechanics also, as I told you, there are two types of approach. One is the relativistic and non-relativistic. So when we are going for a relativistic approach, what? Yes, we need tensors, because in relativity we deal about tensors. So remember that whatever the areas of mathematics you are taking up, please do not take up tensors. Please do take up tensors very seriously. If you want to go into computer programming also, then you need tensors. If you want to study electromagnetism, relativistic, obviously, you need tensors. Fluid mechanics, tensors and fluid mechanics represent stress tensor. And crystallography, I told you that we actually started dealing with tensors in crystals, and material science obviously deal with tensors. So computer vision, in the sense, say for example, you have got a huge amount of data which needs to be stored. You cannot just store it in a hard disk or in general in kind of a flat file system, or even not an RDBMS. You need a tensors where those data are stored up. Somebody, I think Salman was telling you yesterday that Python and data mapping are important. So all these are actually stored in a tensorial matrix form, so that the picking up of the data and mapping of the data is much, much easier. So this actually brings up our reason, very good reason, that why we should study tensors. Okay, are tensors used other than in physics and mathematics? This might be a question to you, that is it only related to physics and mathematics? Yes. So tensors, as I told you, provide a versatile way to represent and work in multi dimensions. That means any huge amount of data, which we call data mining, is actually being taken care by tensors. Deep learning neural network, which is a very upcoming industry here in India and already has taken up the market in US. Tensors are central to deep learning, because neural networks, layers, activations, etc., how can you do that huge amount of data? It needs to be done in tensors. Numerical computation, tensors enable efficient numerical computations in modern hardware, etc. So yes, that means you see the range of tensors are not only in physics and mathematics, but everywhere else. Higher order derivatives, we will see tensor calculus, it takes up tensors. Climate modeling, that means if you are modeling a particular climate, again a huge amount of data forecasting, where will you store? You need to store it in tensors. Data analysis and data mining, again a huge amount of data, sensorial data, etc., where you are going to store? In tensors. Image processing, huge amount. You see, I was watching a documentary where the police used the data in order to draw the picture of a criminal. So how will you use those coordinates and draw it? then it is actually in tensors. So you see, tensors are not typically to physics, mathematics, and only to relativity or stress energy tensor. It actually is around everywhere. Okay, before I go ahead to the origin and history of tensors, I would like to skip this part, and I would like to just a second. Let me see. I think, okay. Yeah, I think I have missed one of these parts. I will go to the origin and history of tensors a little bit later, but just hold on for a second. I need to share one slide so that this part a little bit becomes clear, because I have made a change of this slide, but I forgot to upload it in StreamYard. Yeah. So let me share this part so that it becomes easy for you to understand. I will remove this and I will now share, just a second. I will share the present share screen. Okay. I would like to share this part. Okay. And I think this is visible now. Okay. The invariance in special theory of relativity. Okay, when I say that it is invariance in special theory of relativity, what I'm trying to mean is that I'm going to show you today that tensors means invariance, as we have told. Sir, how do you upload all these representations? Hi, sir. Do you upload all these great presentations somewhere? Who is this? Five Rob. Okay, I don't know your name. No, I don't upload it. I mean to say these are meant for my making my videos, so I keep it to myself. I mean to say that is how I do. I don't, share it anywhere else. Anyway, so what I'm trying to show you out here is that when we learned from the earlier video that tensors are basically invariant in nature. That means whatever the laws of physics happen, tensors will help us to measure those things. And there will be transformation rules, transformation laws, etc. And we are going to make out of that. Now, before going into the tensor calculus and tensor mathematics, I'm going to take you a very simple example. That is the example of special theory of relativity. And in special theory of relativity, this is something which is called a light cone. Okay, so light cone, I think you already know, it is a way of expressing what is called a spatial dimension. Okay, I'm removing myself for a second so that you can have. So gravity has a geometry. Whenever we are tooling, you see that there are actually light cones which tells the present, the past, and the future. Now, say for example, there are three types of events which are taking place. Okay, I am teaching you tensor, but before that, I will just give you an idea of special relativity so that you can understand things better. One is called a time-like events. It is this one. Okay, let me shorten it and let me make it big. I hope you can see this, right? So this one, which I just shortened it, and then this one, this arrow. This is called a time-like event. It is a name. That means these are events that lie within the past light cone, this part, okay, and the future light cone. This means that they can be influenced or can be influenced by or influenced by the observer. Let us understand for the time being. Another event is called space-like event. This one, which I am now moving. This one. This is a space-like event. That means they cannot influence. Why? Because it is standing outside the light cone. Okay. Good evening from Pakistan. Empowering Visions. Very good evening, Empowering Visions. I hope you will like today's lesson on tensors. Very welcome to Physics for Students. And another is which is called a like event. This one, which I'm moving right now. This one. This is called like. They cannot be influenced because it is just lying on the boundary. Okay, so let us understand that this light cone or understanding of the space-time events, I will do it separately in special relativity. Now you see, okay, this you can see. Now, what is this one? Okay, this is what is called a space-time interval. Okay, let me tell you what is a space-time interval. I will just pick up my just a second. I will just pick up this Jamboard of mine, and I will try to explain it very simply. Just wait, I will just share my Jamboard. I will remove this, and I will Okay, I will just remove this and I need to add my, just a second, present, share screen. Okay, yeah. So what do I mean by actually events is that, say for example, anything, any kind of an event which is happening particularly in this frame of reference, okay, and it is in this frame of reference. These are two frames of reference. Okay, for example, there is an event E1 happening over here. This is an event E prime 1 happening over here. This is an event E2 happening over here, and this is E prime 2 happening over here. And the person, sorry for my horrible drawing, I'm just giving an analogy, is called O, and this person who is standing over here is called O prime. Okay, so whatever is happening over here in this particular event, the person sees over here and the person sees over here. So we will soon see the basic idea is that this particular event and this particular event, this particular event and this particular event, as seen by O and O prime, are actually same. That means there is no called a difference in terms of observation. Okay, I will now go back and I will try to show you this one. So you see here what is happening. I'm so sorry, so sorry. Yeah, so this one needs to be discarded, right? Yeah. And I need to add uh, present share screen. What is happening? Just a second. Too much of slides. No, not this one. I want to show this one. So you cannot see this. Just a second. Hold on. Slides. No, I need to share screen. Yeah. Okay, so here you see this one which is happening delta S squared. This is called the space-time interval. Space-time interval basically means, as I told you, the interval between two events which are happening. Now you see this one is called delta x squared plus delta y squared plus delta z squared. Delta x means a finite amount of change, that is from x2 to x1. Delta y means y2 to y1, and delta z means z2 to z1. Why we are calling it delta? Because it is an finite amount of change. If we call it infinitesimal, what it will happen? It will become ds and dy. Okay, now I will come back to my Jamboard and I need to explain you something very important. This will actually show you the real reason that why we call this space-time interval, etc., to be so. Okay, let me remove this and I will stop sharing and I will just present my Jamboard. Present share screen. Yeah. Okay. So what you are going to see over here, I have just made it small. I will just show you one by one. Okay. So this is actually what we saw. Okay, now you see in this equation, if you don't understand this part, why it is minus, I'm going to explain later. But as you can see over here, this is the space-time interval, delta S squared. Okay, this has to be constant. That means that whatever happens, this equation or this space-time interval cannot change. And that is why we are now going to show you how this actually, I mean to say, becomes a kind of a tensor. Now you see the space-time interval can also be given by this one. Okay, I am using dy because I am trying to make a kind of an infinitesimal amount of change. This d square equals to x to 1, this one x to 1, this one and this one. So what I have done is that just I have measured this one. This is this, this is this, and this is this. Okay, and this one has been replaced as this one. This delta t, as you can see, is the change between T2 and T1. I hope you can all get it clear. While the double signs front, yeah, yeah. So empowering vision, if you can put up your name, who are you? Uh, okay, Atharva is telling, thank you, sir. Good, valuable advice. You are right. Good communication, writing, still personal improvement essential. Yeah, and I won't say specialist, but I am a very professional person in making people work for communication skill. No, I won't charge anything, but if you want to learn anything regarding communication, talking, etc., Atharv and others, you're all welcome. Again, I'm a professional, but I really don't charge to you all people because I love to interact with students. Okay, y double signs plus plus in front of delta y squared. Yeah, delta y squared, why we have got double plus signs, I will come to you, I will explain. Okay, now you see what I'm trying to tell is that this equation means this equation, this equations is invariant, meaning that it does not change when the events are viewed from different frames of reference. Different frames of reference means this is one frame of reference, and maybe it is accelerating or it is going in this way, whatever, it won't change. Remember what I told you, again I repeat, the equation is invariant means it does not change when the events are viewed from different frames of reference. This is because of the Lorentz transformation. Now, answering to empower vision, the negative sign is of the space, ensures that the space time is invariant. I will come to that. I will later explain you. First, let me explain what I am trying to do. Otherwise, I will forget. Okay, so what you see right from here is that let us consider that we are not using the negative sign. Okay, we are using the negative sign. First, I will show you what happens using a negative sign. This is the Minkowski metric. I will come to that. And what happens without using the negative sign. Now, this negative sign will actually show you that why we are constantly telling, tensors are invariant, invariant, invariant. I will show you. That is important. I made it for you all. So here you see ds square equals to minus c square d square. That means I am considering this negative sign for the time being. I will show the metric so that you can understand. I am considering this negative sign. Okay, I am underlining this. Okay. Now, first of all, for two events, let us say A and B, you just imagine, because I don't have the place. Here we can draw. This is an event A. This is an event B, which is happening over here. Okay, which are occurring in the same place but at different observers O. For example, if the observer O observed, then he will or she will get this one. Okay, ds square, that is the differential distance, ds square means the differential space, is equals to minus c square delta t square. I think this can you can all understand because this is pure special relativity's time interval equation. The delta t is basically the distance which is happening between the observer, between the event and the observer. Now let us consider another which I told you here, O prime. This person is O prime, right? So let us consider O prime, another observer who is moving at a relative velocity v to observer O. Now, if this person is moving relative to this person, which is observer O, then what we are going to get is this one, this part. Let me drag over here, this one. And we all know what is this. We all know what is this. Can anybody tell? This is the Lorentz factor. This is simply the Lorentz factor, that is the gamma. So what is gamma? It is equal to square root of 1 minus, it would be equal to 1 minus divided by root over 1 minus v square by c square. I don't have the space to write. That is the problem. So gamma would be 1 whole divided by root over 1 minus v square by c square. So this is the Lorentz factor. Okay, this gamma. Fine. Now, after that, the space-time interval for the observer O, what would be? That means the observer O, what will the observer O see? He or she will see this one. Simple, because this will become ds prime. Why it is prime? Because this is the observer, the second observer is the prime observer, means the prime notation. And from here, you see this ds square, just a second, yeah, this one will be, and this one. Now you see the observer O is finding the distance to be this ds square, and observer O prime is finding the distance to be this. Again, let me repeat and write it this one. So for the observer O, you see what is the distance? The interval is this one. This is for observer O, this is for prime, so this is for observer O prime. So what do we see? That comparing these two equations, this and this, observer O, okay, let me write observer O, and this is observer O prime. So comparing the space-time interval between O and O prime, we see that they are different. That means due to the presence of this Lorentz factor, this gamma factor actually has caused a time dilation. Now, this difference in space-time interval actually shows the relative nature of the time. So, if this factor is not present, this and this would have been the same. But it is good that we have got different. Different means that there is a time dilation, and it actually shows that what this person will observe here will not be the same with this person will observe, because the clock will be time dilated. That means it will be running much slower. Dilation means much slower. So this proves actually our fact that time dilation takes place, and what one person watches is not the other person watches. Now I will come to using the Minkowski metric without this negative sign. Now hold on, I am coming to the tensor. You might be thinking it is special relativity. Absolutely not. So what I would like to show you now is that if the negative sign is absent, you see we get the equation as this. You can see simply that the negative sign is not there. So for two events A and B again occurring at the same spatial location but at different observers, this would become this. ds square will be, again absence of minus sign. Okay, it would be this. Now again, if I see that the observer O prime, who is moving with a relative velocity of v to the observer, because there is no time dilation, remember here there was a time dilation because of this gamma factor. Because of this gamma factor, there is a time dilation. That is why these two are different. Okay, this person and this person does not see the same thing. But here, because there is no time dilation, what we see is this. Okay, what we see is this. And if we see this, then the space-time interval for the observer O prime would be this one. Now you see what is happening. This one, this equation, ds prime squared, and let me expand this for you. This one, don't you see both of them are the same? Both of them are the same. You see, for the prime, that means the observer, this is O prime observer, and sorry, this is O prime observer, and this is the O observer. This is the same as this. That means what? That means it shows from here that if we do not have the negative sign, if we do not have the negative sign, so sorry, yeah. So if we do not have the negative sign, then there is no time dilation. That means this gamma factor is not there. And if there is no time dilation, that means these two people would be observing the same thing. And how can it be possible that these two people are observing the same thing? Because special relativity itself tells that the observer who is moving faster, there will be a time dilation. Are you getting my point? I mean to say, I understand that I'm suddenly introducing this factor. Now I will show you the reason. So this and this are both the same. Now the question comes that if these two things are same, and what we find from tensor and the concept of tensor, that things should be invariant. That means there should be a matrix, there should be a component where things really do not change. And here is this thing. Let me show you. This will answer to the person who was asking empowering vision. The Minkowski metric are actually taken up in these two forms. One is a minus, plus, 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 and another is this one, plus, minus, 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 and this looks like this. Oh, sorry, this looks like this. That means if I diagonalize this matrix, if I diagonalize this one, you see minus 1, 1, 1, 1. Okay, and this one, this O prime would be 1, minus 1, minus 1, minus 1. That means this particular equation, let me copy this forward. This particular equation can be written here also with a negative minus sign. I can write it, this one with a minus, okay, and then a plus and a plus and a plus. And same, I can copy this equation over here. And what I can do is that I can write here a 1, this is a plus and a plus and a plus. But remember, this is actually what the tensor is all about. This is called the Minkowski metric tensor. And what does the Minkowski metric tensor tells? The Minkowski metric tensors actually forms the equation in such a way that whether you're using a minus sign or whether you are using a plus sign, this will be the difference. If there is a minus sign, that means it will follow minus plus plus plus. That means it will take up in this way. That means there will be a time dilation. Okay, this observer and this observer are not going to see the same thing. If I take it in a plus way, that means this part, and if I ignore this, then both the observers will be watching the same thing, and this violates what is called the relativistic equation. It violates what is called the space-time dilation. Now, the reason I'm trying to show this is that this actually takes the form of a tensor. Let me go to the next page. This one is a tensor. I will tell you now what it is actually all about. And this one is also a tensor. Okay. And not only that, you will see that sometimes this equation, the space-time interval, in many textbooks, you will see that this particular equation is sometimes written, say for example, with a minus dx, and minus dz, right? And it has got a 1. If it is this, that means it is following this metric. And sometimes it is written just like this. Both are correct. The first one is the usual way. Both are correct. Nothing is, you can say that it is not wrong. That means here it is a minus sign. I'm so sorry. This one, no, this one. Where is the minus one? I should take this one. Yeah, this equation. This equation will be put over here. Why? Because we are following the diagonal of the matrices. Here it is a minus, here it is a minus. Here these are 1, 1, 1, these are 1, 1, 1. But remember, all these these matrices, I mean to say, these are actually called metric tensor. Okay, let me write it for you. This is called Minkowski metric tensor. Minkowski metric tensor. This is also correct. This is also correct. It is not that any one of these are wrong. But what it tells actually, the Minkowski metric tensor, what it actually tells that the elements are arranged in such a way. I mean to say, if I take the invariance part, then the Minkowski metric is basically invariant in special relativity. What do I mean by that? The invariance refers to the constancy, or I would say the constant nature of the space-time interval under Lorentz transformation. That means the Lorentz transformation, that gamma factor actually preserves the form of the space-time interval, ensuring that it remains the same regardless of the observer's frame of reference. That means that if the frame of reference is over here, okay, if the frame of reference is over here, or the frame of reference is over here, or maybe the frame of reference is rotated, or whatever happens, this Minkowski metric is going to ensure that the laws of physics are the same. That means either I am going it in this way, I put a negative sign. Either I am putting it this way, I put a negative over here. The metric will always be the same. Now you see this particular one. This particular one is what? This is n mu nu 0, 0. 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 2, so on. So this is called a rank 2 tensor. Why it is a rank 2 tensor? Because of this mu nu. That means it is a rank 2 tensor. If it was a rank 3 tensor, then it would have looked like n mu nu x. And the values inside the tensor would be, say, for example, t 0, 0, 0. Then it would be t 0, 0, 1. Then it would be t 0, 0, 2. That means 3 indices over here and 3 indices over here. But here what is happening, we have got, this is actually not the value. I have taken the directly matrix, but this is how, this is a rank 2 tensor. We are talking about rank 2 tensor, do you remember? So what actually the Minkowski metric tells, finally let us come to a conclusion. One, why we have found out is that the negative sign, this negative sign If we are not putting over here, that means it is a problem. Otherwise, people will see the same. If I put the negative sign over here, that means there is a time dilation, and this is absolutely okay. Tick. If I don't put up the matrix, then both of these people see the same thing. How can this happen? How can this happen? Because special relativity itself tells that the law, what this person will be seeing, will be something different. And we will put it in a proper metric form, whether we put up minus plus plus or a plus minus plus. This metric ensures that whatever is happening in terms of what we call the laws, the frames of reference, the space-time intervals of observer O and the O actually will be the same. That means what it tells, that it actually preserves the transformation law, and what is called the laws of physics will be the same, or what this person is observing and that person will observing will be the same. So Lorentz transformation, that gamma factor, preserve the form of this space-time interval, ensuring that it remains same regardless of the observer's frame of reference. That means this observer and this observer, whatever they are going to watch will be the same. But if this observer's watch something and this observer's is watching something, the events cannot be the same because of the negative factor. And if the person is accelerating at a speed of light c, then obviously the events will have a time dilation. It would have a time dilation. So this is the reason I thought to express to you that when we are, somebody told yesterday also that when we are talking of special relativity, etc., and we are constantly talking of invariance method, then is it that special relativity can also have a tensor form? Yes, special relativity definitely can have a tensor form, and I just showed you this is what is the tensor of special relativity. If we do it in metric tensor in general theory of relativity, this will become G. This n mu nu will become G. But again, that will be a rank 2 tensor. So now you see, if I want to share my, just a second, I will just stop sharing this one, and I will present the, yeah, present, share screen. Okay, I just share this one. Okay, now you see, when I'm talking, when I was talking about this particular space-like and time-line, and if I go back to my this slide, now you see this slide is actually where it is. Oh, I'm so sorry. This slide is actually, this light cone is nothing but it will be extend to general relativity as the metric tensor G. It will be extended to the metric tensor G, because space-time, Dhruva was telling yesterday that space-time interval, the space-time interval which was measured in light cone, gets generalized to metric tensor in general relativity. Now you tell me why it is extended to metric tensor, because here we measure it by space, time, relativity, etc. But there, what is space-time? Space-time is a curvature. Space-time is a curvature. So there also we find a tensor, here also we find a tensor. Here the tensor is much more elegant and beautiful. The reason is that the tensors actually come in a kind of a Minkowski metric. So what did we learn today? We learned that special relativity, because it is also making that if things move, it will be invariant and changes. If it is talking of invariance, then it has to take into account tensors. It has to take into account tensors. Why? Because without tensors, we cannot make things invariant. I mean to say, the laws of nature. Now you see, space and time has been united into space-time. That is why we are taking tensors. Now you might ask me a question that why Galilean relativity was not included in tensor. You know the answer, because Galilean relativity is not relativistic. If you put Galilean relativity using the speed of light, the equations will fail. That means Galilean relativity cannot be united with something where the things are taking one form together. But in special relativity, very much yes. Why very much yes? Because space and time has been united. And whatever happens, the laws of the nature will be same from all observer. Now here is a confusion. You might be thinking, why I'm telling the laws of nature are same for one observer. Again, I'm telling that the laws of this person observed, that person observed, there is a time dilation, etc. Now remember, what I'm talking about, that is local, the second one. That means the time that that person watches, that the time is slow. Events are taking place much slower. Say for example, the words as it come, it is much slower. That is local. That is what is called the proper time. There are two types of time. But tensors actually tells us that the overall inertial frame of reference for that observer and this observer, both of them are watching, they will observe the same thing. But as per of the local reference which that person observed, the time is running slow. So tensors actually give us, not only in terms of pure mathematics, but you see, I actually calculated and showed you that what is the meaning of that minus sign. That meaning of the minus sign actually promises that the person or the other person is finding time slow and observing things different. If we do not have a minus sign, then the special relativity will frame. Once we frame everything in a proper tensors, that is a matrix, that is this Minkowski matrix. This Minkowski matrix and the negative or whatever, when we put all the values together, I will explain you next day what those minus, zero, etc. means. We will see that the metric or the tensor form itself is something very unique. And if you put in the value, if you are accelerating at a speed maybe 50% of the speed of light, I am just not accelerating anything, the laws of nature or what the observers will observe will be the same. So I am not going to the next details, that why the origin of the history of tensor, because I was in a very mathematical mood today to show you how this tensors. Any questions do you have? If you don't have any question, we can close it, and I will be again online possibly tomorrow, Monday, because Saturday there is a webinar of mine. Monday, Sunday we have got this Dr. Debanjan Bose coming in the evening. So a lot of things happening during these 2 days. So I will be back on Monday, and we will continue with this tensor. So this is basically the idea, the overall concept of tensors, and kind of a trick, a mathematical idea, that how the tensors, rank 2 tensors look like, and why these frames are. So you see, this is a simple example of special relativity, that things will be the same if we are using the tensors. So I think you don't have any question. Tell me in the comment or the chat box, how was it? Is it a little bit difficult today, or was it an easy way out? I would say, have I been able to? Now, if you don't tell me anything in the chat box, it becomes difficult for me to understand what are your reactions. So is it okay? I mean to say, I think you got the point, or was it a little bit difficult? What is the takeaway for today's lecture? Can you just? Informative, yeah, okay. And anybody else who is watching? Vector, momentum, and force shortly. I think that you were talking of the 4-vector part. I mean to say, it actually, I will explain to you next day, because I have to show those equations, and I really feel, so relation between length contraction and time dilation. No, relation means the contraction of the length happens when we are accelerating at the speed of light, and time dilation also happens. I mean to say, these are two distinct events. Who is this inter-resistance? These are all, now we are going to special relativity. Anyway, so these are all actually events which are happening. I mean to say, these are calculations. And all those things are happening once you put that gamma factor. So relation, I mean to say, between length contraction and time dilation, the length contraction happens when we are moving at the speed of light. And okay, and so once this length contraction happens, the same way the time dilation also happens. Tech lover professor, is the principle of equivalence is universal? If so, why? Principle of equivalence depend. Are you talking of the weak equivalence principle or the long strong equivalence principle? But yeah, if it is definitely universal. I mean to say, universal in the sense what? This actually happens, and This is Einstein's basic tenet between the what you call the general relativity, right? That is the basic tenet. So definitely it is universal. It actually, it is a kind of a thought experiment which happens, and based on that we got the factor. Can we connect it with entropy and time? I mean to say, I'm getting confused. Which one are you talking? Relation between length contraction and time dilation. Entropy and time is something different. I mean to say, length contraction is when an object moves at a certain speed of light, it takes place, and time dilation is the stretching or slowing down. I mean to say, when it is near a gravitating body. So that is basically represented by the Lorentz factor, as simple as that. So can we connect it to the entropy and time with entropy? Can we connect it with entropy and time dilation? No, entropy is something different. Entropy is related to the expansion of the universe and the chaos. Entropy increases, which defines the flow of time. Yeah, it doesn't define the flow of time. It is a property. Yeah, it is a property. It increases. And see, I think you're getting confused. See, again, entropy, which defines the flow of time, etc. These are again happening at lower scale, not at the speed of light. I hope interresistance you can get it. Length contraction, time dilation happens only and only when we are speeding at the speed of light. If it is below, nothing is going to happen. It is just going to follow the Newton's laws of momentum. So don't try to compare things on a different scale. If you're talking of length contraction, time dilation, that means you are expecting the particles to move at the speed of light. Is what explained it in previous lecture of astrophysics? I cannot understand which lecture of astrophysics you're talking. Is there something called radiation entropy? Let me think on that. Radiation entropy. Um, Radiation entropy, in the sense, I mean to say, entropy is basically related to thermodynamics. Now for radiation, the entropy, I mean to say, it is related to the number of available modes. So I really cannot get what you're trying to tell. That so what happens in classical physics, considering radiation, if you take in a closed system, then the number of possible states increases with frequency. And in quantum mechanics, this concept is expanded. For example, radiation can be absorbed by photon, etc. So I can say that entropy of radiation is definitely playing a significant role, right, in various physical phenomena, which includes the behavior of strong gravitating bodies like black holes, CMB, cosmic microwave radiation, etc. So what I can tell you, the relation between entropy and radiation is something complex, I would say. So you are merging the concepts of thermodynamics, statistical mechanics with quantum mechanics. That is, I mean to say, that is, I won't say that is not done, but that is something weird. The classical mechanics, thermodynamics, you're mixing with the quantum mechanics. I really cannot get what you're trying to tell. Anyway, so thank you for being and asking so many questions. So we will continue with that. But the basic takeaway today is that, see, what I'm doing is that I'm dividing all those live sessions into classes. So we are learning tensors. So I would request all of you to ask me questions related to tensors only. But you are all welcome. Definitely, you can ask me questions. I love answering these questions. But if it is something related to the learning, then it becomes easier. I mean to say, it becomes very pertinent, right? So hope you liked it. Nobody is putting up any comment after the live section, whether it is good or bad. So I would really request you to put up some comments. It comes as a motivation source also. Right? Radiation is also composed of entropy, I think, so due to the temperature of it. Yeah, radiation is also composed of entropy. Means what? Radiation is radiation which is happening. Entropy is the chaos, that is the order. Now, how do you, I mean to say, my question to you, Tech Lover, is that how are you linking those two things? Radiation means, again, it comes under the quantum mechanics. What are you radiating? The alpha particle, beta particles? Is it a decay or it is a radioactive radiation? And then you're talking of entropy, which is a physical law of nature. I'm still not clear. I think you can better think and later let me know what it is actually. Anyway, I hope that this session is going okay, isn't it? What do you think? That we should engage more in this kind of a discussion? Whether it is right or wrong is different, but we should engage this kind of a discussion, right? What is your opinion? Disorderness in concentrated mass. Yeah, I mean to say, yeah, it is. Disorder is there in a concentrated mass. As a system composed of particles, as a system composed of particles consisting of entropy. I really cannot get what are you telling. Dhruva is telling the session is good. Session is good. Okay. So Dhruva, is this okay? I mean to say, shall we go like this? I'm asking for all your suggestions. I mean to say, is it that we should go like this? Radiation is also a system of photons, so there will be entropy. No, radiation is also a system of photons. No, entropy is taken as a whole. Anyway, you can come to me contact later because I'm not getting, I mean to say, I'm not understanding what you're telling. Is it a mathematical theory you're trying to propose, or it is an equation, or what it is, or it is just a concept that you're bringing from your radiation and then entropy it's together? Can you make a lectures on Maxwell's demon? I will look into this. And nothing in my cards today because I have already got few lectures coming up on. I need to finish up tensors, then follow with general relativity and so on. I'm also planning a series of lectures on real analysis and complex analysis. So no, I just wanted to know, have you all understood what this is about? How the tensors in Minkowski metric is making things invariant, why there is a negative sign which is required, otherwise special relativities will fail. If the negative sign is not there, the same both of the observers are watching the same thing, which is not there, and how this Minkowski metric is helping to get the laws of nature invariant. Have you got it? Yes or no? Tell me. It's already getting 10 o'clock. I should also quit. I have a big day tomorrow. Okay. Yeah. Thank you very much. Okay. So if you get any confusion, you're always free to ask because I want that you should get into this concept. Next, we will start with further with tensors and then we will go into the mathematics of tensors step by step for the vectors, then covariant, contravariant, and then going and deriving up to the metric tensor. Okay. Thank you very much.